Today, artificial neural networks currently interface with the complex physical world around them through a single foundational mechanism, the perceptron. This sensory unit relies on a specific mechanical sequence. It computes a weighted sum of incoming data, followed by a nonlinear activation. This makes the perceptron a geometric classifier. Its primitive operation is a linear threshold event, a projection in feature space that determines whether a signal triggers an output. Biological organisms, however, do not process environmental changes through these types of linear geometric thresholds. Relying on these abstract threshold units forces the initial sensory mapping into a simple monotonic saturation. The network essentially captures a signal's intensity, but misses the underlying mechanics of living sensoria. Cellular receptors detect environmental changes through two-state thermodynamic equilibria. These receptors exist in a constant balance between a high-affinity active state and a low-affinity inactive state. Ligand binding perturbs this equilibrium, shifting the population density to create a biological consequence. The receptor theory suggests that deep learning front-ends can be upgraded by replacing standard perceptron units with these receptor-inspired computational blocks. This transition requires the network to treat sensory input as an effective dose field rather than a raw numerical vector. This shift transforms the first hidden layer from an arbitrary feature embedding into a discretized, biophysically grounded sensorial field. The receptor block introduces a mathematical split by replacing the single scalar activation with two distinct parallel metrics. The first metric, total binding, explicitly computes the sum of the two Langmuir occupancy terms. Total binding represents occupancy, tracking how much simulated stimulus binds to the artificial receptor. The second metric is the net shift, which measures the thermodynamic displacement of the states. Net shift represents efficacy, quantifying the biological consequence of the stimulus independently of total binding. Mathematical decoupling allows a computational system to distinguish between high sensory noise, which drives occupancy, and a meaningful signal, which drives efficacy. A computational simulation compared a standard perceptron unit against the net shift receptor block to see how their response structures differed. The test used a wide stimulus sweep and strongly separated affinity parameters to make the receptor-like behavior easier to observe. The perceptron generates a monotonic saturating response. It behaves as a standard classifier, rising with the input until it reaches a flat ceiling. As the unit saturates, its differential sensitivity decays, leaving no room for nuanced responses at high input levels. The total binding curve from the receptor block shows a similar monotonic saturation. The net shift efficacy curve follows a different trajectory, forming a localized peak that defines a preferred operating range for sensitivity, clearly diverging from the saturated binding curve. This peak shows that the receptor has a preferred efficacy regime. Even while binding remains at its maximum, the actual efficacy of the signal declines. Because efficacy operates in a distinct regime from occupancy, the AI can natively accommodate complex receptor-level phenomena like desensitization without extra hardcoding. To optimize these units in deep networks, a log scale is applied to the net shift output. This connects the model to the Weber-Fechner law of psychophysics, where equal multiplicative changes in intensity are represented as equal additive differences. Applying the chain rule to this log-scaled signal introduces an extra denominator term to the gradient flow, which acts as a dynamic valve for network updates. In regions with large net shifts, this term serves to compress gradients. This prevents high-amplitude sensory channels from dominating the network updates, which is critical for maintaining stable model conditioning. Conversely, in low positive near-threshold regimes, gradients are amplified, ensuring the network remains sensitive to subtle relative changes. This log scaling forces the network to optimize on relative receptor change rather than absolute magnitude, aligning the learning signal with biological psychophysics. The net shift framework provides a different structure for sensory processing, starting with receptor equilibria rather than abstract hidden units. A receptor block layer at the front of a network absorbs raw inputs and translates them through the two-state net shift equation. This layer then passes concatenated channels to higher layers, providing biophysically meaningful labels for both efficacy and occupancy. By carrying both metrics forward, the network allows higher layers to work with a psychophysically compressed signal, while maintaining the mechanistic interpretability of the receptor state. This architecture serves as a strong inductive bias, acting as a generative prior for modeling sensory biology more accurately. These technical improvements raise questions about the nature of synthetic consciousness, particularly regarding what computational models can and cannot achieve. The receptor theory maintains a strict boundary. Simulating the mathematics of receptors does not spontaneously generate biological consciousness. According to this theory, while a deep network can approximate receptor dynamics, true consciousness is tied to biological receptors, metabolism, and redox-sensitive chemistry. The primary value of the receptor block for AGI is its ability to cleanly distinguish abstract intelligence from the biophysical requirements of consciousness. It provides a rigorous route for AI to model receptor-centered sensoria while respecting the distinction between artificial perception and biological reality.